So, welcome my friends, welcome to my next lecture. So, in this lecture my plan is to talk about, of course, coming couple of one or two lectures including today's lecture. So, now the topic is actually I want to talk about line integrals, so concept of line integrals. Okay. So, line integrals, and that means for that I need to define what do I mean by smooth curves, contours and oriented curves. Then I will talk about the notions of what is called scalar line integral and then vector line integral and couple of properties. Now, if you remember in my last lecture when I talked about like curl, divergent, so Laplace operators in my last couple of lectures, and you see I introduce the kind of integrations, and that time I said that I will have more on this vector line integral. So, now it is the time to talk about vector line integral, but before that I should talk about what is called scalar line integral. Okay. But before to introduce the notion of scalar line integral, I need the notions of what is called smooth curves, contours, oriented curves. Now, if you remember at the beginning of my lectures, I think in the first week or second week, maybe I think if I remember correctly, I have introduced the notions of curves, smooth curves and contours. So, maybe if I want to talk about the notions of scalar line integrals. So, I thought that let me just recall this once again very briefly, and then I will talk about the concept of scalar line integrals, couple of properties, examples, and then I will talk about what is called vector line integrals, couple of properties and examples. So, that is the plan for couple coming 1 or 2, 3 lectures. Okay. Okay, so that is the learning outcome. So, for coming 1 or 2 or maybe 2 or 3 lectures. So, I will introduce the notions of what is called smooth curves, and then of course, finding the tangent vectors to the smooth curves, and then I will introduce the notions of scalar line integrals for smooth curves, and then I will talk about what is called orientations of smooth curves, and then finally, I will talk about what is called notions of vector line integrals over oriented and smooth curves. Okay. So, that is the kind of brief outcome of coming 2 or 3 lectures. Okay. So, let me just start with the notions of curves in Rn. Okay. What is that? Okay. So, what is curve? Now, if you remember, I think that notions of curve I already discussed in my very beginning, when first week or second week of lectures. Okay. Let me just recall once again. So, the title is actually curves in Rn. Now, a curve, like what is the definitions? So, I am saying that a curve that I am denoting generally as capital C. So, a curve may be thought of the graph of a continuous function from an interval I subset of R to the space Rn. So, if I want to talk about the curves in n dimensional Euclidean space, that means the function should be the range of the function should be in that space, in Rn, that n dimensional Euclidean space, but the domain should be some interval subset of R, and the function should be continuous. Okay. So, a curve C may be thought of the graph of a continuous functions from an interval I subset of R to the space. Now, that interval could be whole real line, that could be the case. Okay. So, for example, okay, what is an example? Suppose you have an interval I subset of R, then the graph of a continuous functions I am denoting as what is the continuous function capital R, which is defined on some interval I subset of R. This is the interval I subset of R to the range in Rn. That means, where I would like to say that curves in Rn, range should be in Rn, but domain should be of that continuous function should be some interval subset of R. Okay. So, as I said, so it represents a curve in Rn, and once I have that one, then I am saying that the functions capital R of t, where t running over this interval I is called the parametrization of my curve C. Okay. So, a curve C is nothing but the graph of a continuous functions from some interval I subset of R to Rn, if I want to talk about curve in Rn. And once I have that functions capital R, so R of t for t running over the interval I is called the parametrization of my curve C. If I give examples, then it will be more clear. For example, look at the first example. So, it says that if I have these functions, what is these functions? So, capital R is a map from your closed interval 0 to 2 pi, which is subset of R to R2. Okay. So, what sort of map it is that? So, if t goes to what is cosine t comma sine t. So, this is the curve. Of course, so it is a continuous function, right, because I know that if I have a functions from say some interval R subset of some interval I subset of R to R2. So, how many components? It will have 2 components. So, R is equal to, you can say, right, F1 comma F2. Okay. What is my F1 in this case? So, F1 t is nothing but cosine t and F2 t is nothing but sine t, right. Now, what is the meaning of the continuous functions capital R? Then if the component function is continuous, I already talked about when I talked about that vector valued functions of say real variable. There you can write your functions as n components if my functions is Rn valued, and if each of the component is continuous function, then I can talk about capital R is continuous. So, now here f1 f2 both are continuous functions because f1 is cosine function which is a continuous function, f2 is a sine function which is a continuous function. So, f1 comma f2 is a continuous function, and therefore your corresponding functions R is continuous functions. Okay. Once I have a continuous function, so that means it will give you a curve, and if I draw the picture of this curve in R2, or what is this? This curve is nothing but in R2 the image of this R in R2. So, R is a map from closed interval 0 to 2 pi to R2, right. The image of this R of the closed interval 0 to 2 pi is nothing but if you draw it, it is a circle. It's a circle with center 0, radius 1, unit modulus. Okay. So, this is a curve. Okay. And this R2 is called the corresponding parameterizations of this curve. Then another example is, if you remember the similar kind of picture I already drawn in my earlier lectures, like this is, if I have this curve RT which is a curve in R3, right, whose first component is cosine, second component is sine, and third component is t. So, if you draw a picture in R3, it will be like what is called circular helix. Okay. It is a curve in R3 because it maps interval, here interval actually full real line R2 R3, and if you draw the image in R3, it is be like circular helix, if you remember. So, that kind of circular helix I already talked about. And of course, this is a continuous functions because R has 3 components. So, in this example your R has 3 components f1, f2 and f3, right. What is my f1? f1 of t is nothing but cosine of t, f2 of t is nothing but sine of t, and what is f3 of t? f3 of t is nothing but t. So, this is a continuous function, this is a continuous function, this is a continuous function, right. I have each component function is continuous, therefore, capital R is a continuous function. So, therefore, it will give you a curve since the value is taking in R3. So, it will be a curve in R3, and if you draw the picture, it will be a circular helix in R3. Okay. And last one, these are not the last one, this is another example. So, what it says, if I take a point x0 in Rn and x1 in Rn, suppose I am taking 2 points, suppose I have a Rn dimensional, take a x0, take a x1, okay. Then you just draw a line segment joining the point x0 and x1. So, if I have to write it in terms of parameterizations. So, then the equations are t, which is t times x1 plus 1 minus t times x0, where t running from 0 to 1. So, this will represent a straight line joining the point x0 and end point. See, because if I put t is equal to 0, then what will happen? This will not survive. So, only this will survive. So, at t is equal to 0, what is the point? It starts with the point x0. Okay. So, it start with the point x0, and suppose this is my point x0 to x1. So, that is a straight line. Okay. And t is equal to 1, it is the end point, and if t is equal to 1, then that will not survive. So, only x1 will survive. So, it is a line segment, and if I have the directions, it starts from x0, ends at the point x1. Okay. So, that is a straight line joining x0 to x0. So, that is also a curve. Okay. So, you can easily say that is a very nice functions because you can write it x0 and x1 because it is a fixed point. So, each of the component you can write it, and you can write this is nothing but a polynomial in t, right. So, R1 is nothing but f1 comma f2, f1 is a functions of t, f2 is a functions of t, and both of them are polynomial. These are continuous functions. So, therefore, capital R is continuous function. So, therefore, it will be a curve in Rn, and it is a straight line. Starts points is capital X0 and end point is capital X1. So, these are the various examples of curves in Rn. Okay. So, first 2 examples actually curves in R2 and R3. The last one is the examples of curve in Rn. So, that means if I just combine everything, so a curve in Rn is a continuous function from some interval I subset of R to Rn. Okay, that's it. Once I have the notions of curve, then I can talk about the notions of what is called smooth curves. Okay. What is the definition of smooth curves? Okay. So, that is the kind of heading. So, smooth curves in Rn. So, what is the definition? So, a curve in C in Rn. So, definition of curve you are familiar with. I will say that that curve is smooth. Now, once I talk about curve, so then it will have a parameterization, right. Suppose a curve C is in Rn is smooth if C has a parameterizations R, say from sub interval I subset of R to Rn, where I is open interval AB or closed interval AB or left open right left close right open right close or full interval R, such that the following 2 conditions should be satisfied. What about the first condition? That means the derivative of r should exist and it is a continuous at each interior point. So, that means of course, curve means what? Capital R is a continuous function, that is always there, but on top of that I want that it should be smooth. That means the R should be differentiable. Not only that, the derivative should also be continuous at each interior point of the interval I, and not only that, the derivative should be non-zero at each interior point of I. If that is the case, then I will say that my curve is a smooth curve in Rn. Okay? So, that means a curve in Rn, I will say that it is smooth. Now, once I talk about the curve in Rn, then it will have a parameterization. So, let it be parameterization is capital R acting on some interval I, subset of R to Rn. So, that is the continuous function I want to talk about. Now, I say that this curve is smooth if that capital R is differentiable, that means capital R prime t exists, and not only that, derivative also should be continuous. So, it is also should be continuous at each interior point of I. Not only that, R prime of t, that means derivative should be non-zero at each interior point. Okay. If these two things happen, then I will say that that corresponding curve is a smooth curve. Example, let us see some example. So, for example, the first one. So, first one example is that R of t, this is the parameterization is given. So, I mean this is the corresponding map. So, R is a map from closed interval 0 to 2 pi subset of R to R2, right. This is my curve, and how it maps, t goes to a cosine t comma a sine t, right. Now, you can easily kind of draw a picture in R2, then what curve I want to talk about. Of course, this is a continuous function, right. What is the first component? So, if I write it capital R as say f1 comma f2, what is f1? So, f1 of t a cosine t and f2 of t what? A sine t. So, f1 f2 are continuous functions. So, therefore, this is a continuous function. So, therefore, it will be a curve in R2, and if you draw a picture, what is that curve? It is a curve which centered at the origin and radius is a, that is the only thing. Okay. Now, this is a smooth curve. Why? Now, R is differentiable. Now, if you know, I already discussed that if I have a functions, say which is vector valued functions from say variable R, domain is R. So, that function, that sort of functions is differentiable if and only if each of the component function is differentiable, right. So, now R has a component f1 and f2, and f1 f2 are nice function. F1 is a cosine function and small f2 is a sine function. Small f1 and small f2 again a differentiable functions. So, what is the derivative? Small f1 derivative, this is nothing but minus a sine t, and what is f2 prime is a cosine t. So, therefore, small f1, small f2 both are differentiable. Not only that, derivative also cosine function and sine function, these are continuous functions. So, therefore, in other words, your capital R, which is a differentiable functions and derivative is continuous, that means the first condition is satisfied. Number 2 is that I have to show that R prime t should be non-zero at each interior point. Now, that means interior point means what? T running from 0 to 2 pi, that means if t runs over open interval 0 to 2 pi, I have to somehow show that R prime of t, which is nothing but f1 prime t comma f2 prime t, and what is this? f1 prime t, f1 is a cosine t, that means minus a sine t comma a cosine t. So, I have to show that this should be non-zero, and that is quite clear because t running from open interval 0 to 2 pi. So, if t running from 0 to open interval 0 to 2 pi, if I varies t, so this is always non-zero, that means one of the components should be non-zero, that means at a time that cannot vanish sine t and cosine t, right. So, therefore, it is always non-zero at each interior point. R prime t exists, not only that, R prime is also continuous, that means first condition satisfied, second condition satisfied. So, therefore, it is a smooth curve. Okay. Similarly, you can have this one a cosine t, b sine t. So, first one is a circle, right. I have same a, but also this is, if I change that a and this is b, that is also a smooth curve. Okay. Why? Because these are the component function, this is f1, this is small f1 and this is small f2. f1, f2 are continuous functions. So, that will give you a curve in R2. This is also differentiable, and derivative will be minus a times sine t and b times cosine t, that is also continuous. So, therefore, R prime t exists and R prime t is continuous, and also R prime t is non-zero because it is a cosine a minus a sine t, b cos t, and if t runs over open interval 0 to 2 pi, this is condition satisfied. So, therefore, this is also a smooth curve. What is this? Third example, again this is actually, if you remember, if you look at the definitions, so this is the first component, right. So, that means this is a, what happened means I mean functions from what? 0 closed interval 0 1 to R2. So, that means I am in R2, right. So, if I draw a picture, it will be like, suppose this is your point x1 and x2, and suppose this is my point say y1 and this is y2. So, what is this? So, first component, that means t x2 plus 1 minus t times x1, that means I am talking about the line segment joining x1 to x2. And what about this one? This is again a line segment joining the point y1 y2. So, that means actually if we draw a picture, so it will be like this is the curve, because this is the first component. So, this is the curve actually I am talking about. Okay. This. Okay. So, that means RT. So, this is a smooth curve. Of course, it is a smooth curve. Why? Because what about the first component? So, that means this, in this case, first component is f1t. So, if I write it, so this example, if I talk about this example, so if I write it as f1t comma f2t. Okay. So, what is this? So, where f1t is nothing but the line segment joining x1 to x2, 1 minus t times x1. And what is my f2t? This is nothing but a line segment joining y1 to y2. So, that means t y2 plus 1 minus t y1. So, first observation is that this is a polynomial in t, this is a polynomial in t. So, therefore, f1 and f2 both are continuous functions. Also, it is a differentiable functions. So, therefore, my capital R is differentiable. And what is my capital R prime of t? So, this is nothing but if I just take the derivative, that means f1 prime t comma f2 prime t, right? And f1 is there, f2 is there, you just calculate the derivative. What is the f1 prime t? f1 prime t, if I do it, so that means x2 minus x1, x2 minus x1, and f2 prime t means what? This should be y2 minus y1, right? And this is constant, and constant function is again a continuous function. So, therefore, r prime t exists and r prime t is a continuous function, right? So, therefore, r prime, so that is the first condition satisfies, and r prime t is also non-zero because x1 is different from x2 and y2 is different from y1. So, therefore, this is also non-zero, this is also non-zero for all t in open interval 0 to 1, and r prime t exists and these are continuous functions. So, therefore, this is a smooth curve. Okay. Similarly, if I have this example r t is equal to t comma t square, that is also a smooth curve, right? Now, if I draw a picture in R2, what kind of curve? So, it is actually now this time actually the interval is full R. Okay. Now, if I draw a curve, if you can guess what curve it will give, I think it will give a parabola, right? So, that means so what the y is equal to, so this means y is equal to x square, right? X is equal to t and y is equal to t square. So, therefore, y is equal to x square. So, that kind of curve it will give. So, now in terms of f1, f2, so this is my f1 functions and this is my f2 functions. Both of them are polynomial functions. So, both of them are continuous, both of them are differentiable, in fact, infinitely differentiable. Derivative is continuous function. So, therefore, r prime t exists and r prime t is continuous. And if I consider the r prime t, what is the derivative? This should be 1 comma 2t. Okay. And if t runs over whole R, at least the first component is always non-zero. So, therefore, r prime t is non-zero. So, therefore, it can satisfy these two conditions. So, therefore, it is a smooth curve, and if I draw a picture, it will be like this one, y is equal to x square. So, this was a smooth curve. Similarly, this last example, so the r t is equal to cosine t, sin t and t, this is also a smooth curve. Why? Because what is my f1? So, this is my f1, this is my f2, this is my f3. So, I have component functions f1, f2, f3. So, first f1 small f1 is cosine t, small f2 is sin t and small f3 is t. So, now this is a functions of sine, cosine and t. So, therefore, if I take, so of course, this is a continuous functions, these are differentiable function, derivative is also continuous. So, therefore, r prime t exists. What is r prime t? So, r prime t should be minus sin t, then you have a cosine t and then you have a 1, right? This is my r prime t, and this is also a continuous function. So, r prime t exists, this is also continuous because this is a continuous function, this is a continuous function, this is a continuous function. And of course, it is non-zero because at least the last component is 1, which is always non-zero. So, therefore, this is non-zero for all t in R. Okay. So, therefore, it satisfies this and this, and therefore, it is a smooth curve. Okay. Fine. So, in other words, there is a kind of observation, you can write it. So, smooth curves is a curve without any sharp corner. So, that means it should be little bent. So, there should not be any sharp corner like mod x kind of things. There should not be any sharp corner. It is not that sharp. So, it has to be like that. So, that means it should be little flat in this case. So, there should not be any sharp corner. So, these are the what is called smooth curves. Okay. So, then there is a notion of what is called piecewise smooth curve. What is piecewise smooth curve? A curve C in Rn is called piecewise smooth. From the definition you can see it is not smooth fully, but I can have a smoothness, or in other words I can chop it into finitely many pieces and each of the piece is smooth. In other words, a curve C in Rn is called piecewise smooth if C is composed of a finite number of smooth curves C1, C2, Cn. That means, if I start with a finitely many smooth curves C1, C2, Cn, and I have to add it. So, that means, I have to add in such a way so that end point of Ck should be the initial point of Ck plus 1. And the combinations the curve I will get, that we will call the piecewise smooth curve. For example, this one. So, look at this example first. So, therefore, suppose this is my C1, this is my C2 and this is my C3. So, C1 is the line, this one, C2 is this line and C3 is this line, right. So, if I take C, which is C1 union C2 union C3, so this is a piecewise smooth curve. Why? Because you see, so what is the, so first of all, it is a combinations of smooth curves. So, each C1, C2, C3 is a smooth, because this is a straight line, this is a straight line, this is a straight line, it is a smooth curve. And I have to join in such a way so that the end point of C1 should be the beginning point of C2. That is exactly the case. Now, end point of Ck should be the initial point of Ck plus 1. Now, what is the end point of C1? So, if I go start from here, if I go in this direction, so this is the end point of C1 and which is nothing but the beginning point of C2. So, it satisfies this condition. Similarly, the end point of C2, which is the beginning point of C3. So, therefore, it satisfies these conditions. Each C1, C2, C3 is smooth. I just observed because it is a straight line. So, therefore, it is called piecewise smooth. Piecewise smooth means what? So, it is actually smooth, but smoothness break at finite many points. Where the smoothness breaks? These are the possible points where your smoothness breaks, because it is a sharp corner. So, it is not smooth fully, but it is smooth almost everywhere except finitely many points. In other words, start with finitely many smooth curves, join in such a way so that the end point of Ck should be an initial point of Ck plus 1. Similarly, here suppose if I start with a point, suppose this is my C1, this is my C2, this is my C3 and this is my C4. Okay, if I have it. So, therefore, C, which is C1 union C2 union C3 union C4, is a smooth curve. Why? You see, each of them are straight lines. So, all of them are smooth, and I am joining in such a way such that the end point of C1 should be a initial point of C2, end point of C2 should be initial point of C3, end point of C3 should be an initial point of C4. So, that is a kind of piecewise smooth curve. So, that is another example, and this is also another example, like this is straight line, draw here. And then this end point of C1 is again a starting point of C2, then you have a C3. So, it is a smooth curve because each of the straight line is smooth and joining in such a way such that end of Ck should be initial point of Ck plus 1, and that is exactly going on, and this is the kind of example of piecewise smooth curve. In other words, these are the possible points where you might not have the what is called smoothness. So, that means it is almost smooth almost everywhere except finally many points. Couple of examples. So, boundary of triangle region, that means the triangle, that is a piecewise smooth rectangular path. So, this is the triangle now. So, this is the triangle. So, that means this curve is piecewise smooth. Okay. Then rectangular path. So, this is also a piecewise smooth. Okay. Polygonal path. So, polygonal path, this is also finitely in line segment. So, that means this. So, I am starting with point here, going there, going there, going there. So, this is a polygonal path, this is polygonal, right. That is also piecewise smooth. So, that means piecewise smooth curve means I have a finitely many smooth curves and I have to join them, join in such a way so that the end point of Ck should be an initial point of Ck plus 1. So, this is called piecewise smooth curves. That means I can have the curve, I can chop into finitely many pieces and each of the piece is smooth. I mean, I might not have the smoothness, only finitely many points. Once I have the notions of piecewise smooth curve, then of course, this is I already discussed. Anyway, I should discuss once again how to calculate the length of a piecewise smooth or smooth curve. Okay. So, this is the definitions. So, let C be a piecewise smooth curve with my parameterization, say C is by gamma t, t running from closed interval A to B. Then you can have the formula for length of this curve C, which starts from the points gamma A to gamma B. Okay. So, therefore, I have a gamma. Okay. I have a piecewise smooth curve. Okay, C is a piecewise smooth curve in some space, n dimensional Euclidean space, and suppose this is my corresponding parameterization is gamma. So, that means if I have a parameterization gamma and t running from A to B, that means in the n dimensional space I have a curve whose starting point is gamma of A and end point is gamma of B. Now, what is the length of this curve? Okay, so that length of this curve, that is exactly I have written. So, let C be a piecewise smooth curve with parameterization C. The length of the curve C from the point gamma a, because in the space Rn it is a map from closed interval AB to Rn. If it is n dimensional curve, it should start from the point gamma a to gamma b, and what is the length? So, length, this is the formula. So, it should be up to integrate this object gamma prime t from A to B. Now, of course, it is a smooth curve. So, therefore, gamma prime exists. Of course, it will not exist because if it is piecewise smooth, only finitely many points. So, but it will not affect in the integrations, and therefore, if I take the norm of this gamma prime, because gamma prime t exists and continuous except finitely many points. So, norm is a continuous function. So, therefore, this is a continuous function, and so therefore, this integral always exists, okay, because of piecewise smooth. Since he is piecewise smooth or smooth, if it is smooth, then perfectly all right, because gamma prime t exists and it is a continuous function. Okay, so gamma prime t, so t goes to gamma prime of t, it is a continuous functions, okay, and norm is also a continuous function. So, therefore, composition of two continuous function is continuous functions. So, therefore, norm of gamma prime t, it is a continuous functions, and therefore, the integral exists. So, therefore, I am saying that the right hand side makes sense, and whatever value we will get, that is nothing but the length of the curve. Now, instead of smooth curve, if I talk about say piecewise smooth, then what will happen? This is actually a continuous functions, because this function t goes to gamma prime t, this is continuous except finitely many points, right, because piecewise smooth except finitely many points you do not have the smoothness. Similarly, this function is almost continuous, that means it is continuous function except finitely many points, but which will not affect the integration. So, integration is always exist, and since your interval is t from a to b, closed and bounded interval, in fact compact. So, therefore, this integral always exists, and whatever the value I will get, that is called the what is called length of the curve C from the point gamma of A to gamma of B. So, one example it is there. So, like for example, find the length of the curve whose parameterization is given from closed interval t running from 0 to 2 pi. So, that means this is a curve in R3, because it is 3 components, right. So, first component is f1 is, so suppose this is f1, this is f2 and this is f3, right. So, what about the components? So, this is f1 t is cosine t, f2 t is sine t and f3 t is t. So, I want to suppose find the or calculate the length of the curve. So, what you have to do, you just take the derivative first. So, gamma prime, of course, this is f1, f2, f3, f1 is a differentiable functions, f2 is a differentiable function, f3 is a differentiable function. So, therefore, gamma is differentiable. What is the derivative? Derivative is nothing but, if I calculate the derivative at t, which is nothing but f1 prime t, f2 prime t and f3 prime t, right. So, if I do the derivative, then what is this? So, f1, so f1 prime t, so that means this is f1 na. So, that means this is minus sine t. f2 prime t, that means f2 is sine t, that means this is cosine t, and last one is 1, okay, for t running from 0 to 2 pi. Now, you have to calculate the norm of gamma prime t, which is nothing but, of course, Euclidean norm I am talking about, square root of minus sine t square plus cosine t square plus 1 square. It will give you square root of 2, because sine square t plus cosine square t is equal to 1. So, this is a constant function. So, if I want to integrate 0 to 2 pi, because t running from 0 to 2 pi, I will end up with this value, 2 times square root 2 times pi. So, this is the length of the curve. So, using this formula, you can calculate the length of a piecewise smooth curve or smooth curve with parameterizations gamma. Yeah. Okay, couple of formulas I have given. So, suppose if I have a smooth curve C in R3, that means suppose it will have a parameterization gamma from some interval subset of R to R3. So, that is I have written, suppose has a parameterization C gamma whose first component is x, second component is y and third component is z, where t running over the interval closed interval a to b. Then you know the since it is a smooth curve, so therefore, gamma prime exists and it is continuous. What is my gamma prime? If the what is the component of gamma? X, y, z. So, what is gamma prime t? That means x prime t, y prime t, z prime t. So, that means gamma prime t is x prime t, y prime t, and z prime t. Now, if I calculate the norm, that means Euclidean norm, that means this is x prime t square plus y prime t square plus z prime t square root. And what is the length? So, length is nothing but integration a to b x prime t square plus y prime t square plus z prime t square root, and you have to integrate with respect to t variable. Right. So, that is the formula for length of the curve whose parameterization is given by gamma, and if the gamma is given by x, y, z. So, this is the corresponding formula. Similarly, if I have a smooth curve C in R2, you have a formula. Suppose you have a curve in R2, that means suppose it is given by the parameterization gamma whose first component is xt, second component is yt, then you just calculate gamma prime t, which is nothing but x prime t, y prime t, calculate the norm of gamma prime t, which is square root of x prime t square plus y prime t square. So, this is the corresponding formula or length of the curve if my curve is in R2 whose parameterization given by gamma whose first component is x, second component is y. So, this is the formula. Okay. So, this is in R2, this is in R3. So, this is in R3, right, and this is in R2. Okay. So, now I think I have discussed what is called at least the notions of curve, notions of smooth curve. Then if I have a piecewise smooth curve or smooth curve, what is the length, how to calculate the length, those formulas I have defined, and I have the notions of at least curve, smooth curve. Once I have the notions of smooth curve, then I want to talk about what is called scalar line integral over the what is called piecewise smooth curve in Rn. Maybe I think in my next class I should talk about that. So, that means in this lecture I talked about the notions of curve, smooth curve, and then I talked about the piecewise smooth curve, then length of the smooth curve or piecewise smooth curve, and couple of examples I talked about. So, now I have the notions of smooth curve. So, now I am in a position to talk about what is called the notions of scalar line integral over if I have a smooth curve or piecewise smooth curve. I think in my next lecture I will talk about that, and then once I will define the notions of what is called scalar line integral, I will talk about couple of properties of scalar line integral, couple of examples, and then I will talk about what is called the notions of vector line integral, couple of properties of vector line integral, and couple of properties. So, that is the plan. So, I think I should stop here. In my next class I will start by defining what do I mean by scalar line integral over smooth curve or piecewise smooth curve in Rn. Okay. I think I should stop here. Thank you.